I'm going to talk about the multicore API we have in IncludeOS. Also going to do a little fibers versus coroutines shootout. There was a talk on the first day, Rainer Grimm, called Threads and Locks Must Go. That's a good, I was glad to see that. In this talk, really gonna see threads just go. No threads at all. So, are you familiar with IncludeOS? Okay. Not that many. IncludeOS is a library operating system, and it's designed to run one single process at a time. So that makes it useful for servers and embedded. Also other use cases, but I don't have time to explain that much about what IncludeOS is. I've given a couple of talks about that in the past. But suffice it to say, we take your code, we compile it, we add a bootloader if necessary, and we essentially make your program, your C++ program, bootable. Okay, so that's the concept. We bake, statically link in everything you need from the operating system, and then that becomes a bootable executable. So it's 0% Linux, everything is C++, all the way down to hardware. Some places you have to do some assembly. We try to do as little as possible of that. But for example, privilege instructions, you have to do them with assembly. So there's no way to get all of C++. But there's no C layer underneath us. So let's try to control all your CPU cores directly with C++. Are you doing that already? Anybody's doing that? Are you using some kind of C operating system interface? Or are you just using a lot of abstractions and you don't really know who controls the cores? I'd like to give you the control of the cores directly. So do we need threads for that? Anybody put things on other cores without using threads? A couple of people? Yeah? That's cool. Most people, I think, would use threads to enable all these cores. So I got this email. This is an email from a guy, and the subject was IncludeOS rocks. So that's great. That's a good reason to open an email. But he has this observation about threading. And it says, you know, usually threading is just a way for people to do blocking calls. Does anybody recognize that? Anybody who started a thread in order to do a blocking call? Yeah. I think, unfortunately, some people do that. So I read this email and, oh, realized Santa Claus isn't real. That's unfortunate because, you know, who stole that F-16? I mean, he said he was Santa Claus, but he can't be if Santa Claus isn't real. Of course, the interesting point here is that, you know, some threads are being overused. Classical threads are being used for so many things. It's just the golden hammer that you have for doing stuff like concurrency, etc. Right? There are some good reasons for using threads, but there are also bad reasons. So I was surprised to see that, you know, he says, you know, people want to block to their heart's content. So I imagine this guy. This is a guy who's been writing blocking calls all day. You know, is that how it makes you feel? Who likes blocking calls? Nobody. A couple of guys. I mean, maybe it's kind of a guilty pleasure people have to do blocking calls. I mean, I'll just do something quick and dirty. I know I'm supposed to do async, but you know, for this example, let me just use some fread or something to just get the data. You know, wait for it. I mean, I don't mind the blocking calls, but it's a horrible, costly thing to do if you think about it. It's very costly. You do a blocking call, you expect the operating system has to do quite a lot of work just for you to be able to sit right here. You know, I'm just going to stand right here and wait. You know, if the CPUs are going to be kept active, obviously somebody has to then move you to the side and move somebody else in, etc. So in IncludeOS, we have no blocking anywhere. Everything is event-based. I've done talks about this. This is our IP stack. We lay out all these connections between the protocol handlers using delegates. It's a type of callback, but in our code, often we try to make it so that it looks more like you're just attaching one event to an event handler, and it doesn't really look like this horrible callback syntax where it looks sequential, but it isn't. So we like this system. We don't really need threads or blocking calls at all. Nowhere. It's all event-based. And we get good performance. Thousands of concurrent connections. We're beating Linux on throughput, etc. But unfortunately, these blocking calls are part of the standard. If I want to have people use IncludeOS, we want to align ourselves with the standard, right? You have libc, lots of blocking stuff in there. We can't just ignore them, I think. We can't just ignore legacy code, although for our purposes, we don't really need these blocking calls. So we're going to try, and makes people so happy to do blocking calls. So let's see how we can do it. But first, I want to talk about these threads, which is one way to facilitate blocking. If you think about suspending and resuming, threads is, of course, the most obvious abstraction to consider. Stud thread is also part of the standard, so we should consider supporting that, even though we don't strictly need it for our own purposes. So what are threads really? I mean, I actually started Googling. Of course, I know what threads are. I've been using threads a lot, POSIX threads, other kinds of threads. I've implemented threads. I've implemented processes, context switches, preemption. I have a okay notion about what a thread is, but it doesn't seem to be some wide agreement about exactly what it is. So Wikipedia has this horrible explanation, I think. It says a thread is the smallest sequence of programmed instructions that can be scheduled. That doesn't sound right. Smallest sequence, does that mean it's a very short sequence of instructions? And it's defining a thread in terms of what can be scheduled. But then it goes on to define a scheduler. A scheduler also has a very abstract definition. It just means dispatching or putting jobs onto resources in some way. So, if I just had an array of functions and I iterated over those functions and executed them in some order, that would qualify to be a scheduler. Stack Overflow has one popular answer. Somebody's saying a thread isn't anything more concrete than a set of register values. Well, is that true? I don't know. Who agrees with that? I mean, to a certain extent, yes. You expect that an execution context has to preserve registers, especially if they are preemptive, obviously. You're in the middle of a calculation, somebody preempts you, and then you start doing other calculations, you resume back, and then your registers are all blown. That doesn't work. So clearly, for preemption at least, you need to preserve the full state of the CPU. Intel manual doesn't really help. Well, Intel manual, of course, is super precise about what the Intel processor is doing, but it doesn't really define threads. I think they avoid that. They define tasks. So you can use the CPU to actually do context switches. You can tell the CPU, you give it a struct and say, this is the context that I want to switch into, and it will do that for you. And it's very fast, but it's not as fast as other solutions because it's very thorough. So the Intel context switches or the hardware context switches will preserve absolutely everything, and sometimes you really don't need everything. I talked to Gor Nishonov, the guy who was implementing the coroutines, and he says, a stackful coroutine, that's actually a thread. Okay. So the idea of what a thread really is, isn't that easy to get to the bottom of. And of course, what I'm looking for is how to implement something that can be a backend for stud thread, right? And what's a backend for stud thread? Well, unfortunately, those are Pthreads. That's the POSIX threads. At least in the versions that I've tried, we use Clang and libc++ from LLVM. You just want to create a stud thread, well, there's a call to Pthreads underneath. So we have to implement Pthread interface. So this is something I can understand. I mean, I can understand a function signature of create thread, but it doesn't really tell me what this thread is or what's going to happen with it. You know, is it going to run on other CPU? I mean, yes. I mean, if you start 10 threads and you have 10 cores, usually you'll see them all get active, right? But do you know? Do you have a guarantee? I mean, you just leave that to the operating system, right? But you guys are C++ systems programmers, or at least many of you are. I think you write C++ because you enjoy having control. So I think, you know, it's kind of nice to look at opportunities for providing something less opaque. So do you know if it's going to be preempted? Is it going to be suspended at some point? What if there are too many threads running? Do you control the scheduling of those threads? Who are getting the priority and who are not getting the priority? Do you have control? I don't know. I mean, Linux provides facilities. I'm sure Windows provides facilities for doing some control, setting affinity to CPUs, etc. But that's usually something you do from outside. There are also C APIs for it, but nothing I've seen that's really standardized. Well, yeah. So it gives us a lot of flexibility, this simple POSIX API. I don't like the POSIX API for many reasons, but at least it's something that's quite easy to understand. You have a function signature, you provide a body for it. It's an explanation in the documentation saying what you should expect, so we can try that. So some reasons for using threads, blocking calls, it's not a really good reason because it's an overhead. It's a very unnecessary overhead. But sometimes, if blocking calls, you absolutely have to do them, but you also have to do something else. I can understand, you know, might be a reason for having a lot of threads. Responsivity and deadlines, that's a reason for doing preemption. You know, if you really have deadlines and you're tight on the CPUs, you are overbooking a CPU with several tasks. One task has to do a very heavy computation, but you also have to be responsive in your UI for letting the people click buttons, etc. You know, and you're constrained so that you have to do this on the same CPU. Well, then, of course, preemption sounds like a reasonable thing. Also for deadlines in real-time operating systems, etc. Parallelism over multiple cores, that's also one reason. We're going to see that we don't really need threads for that use case. So let's just go through how we access the CPUs, and this is all x86. It's what we're targeting. I would like to be on ARM, so if somebody is interested in doing a port to ARM, please come find us. So you have all these cores, and you have the bootstrap processor. That's just the first CPU. I don't know, maybe it's defined in the BIOS or something which CPU that will be, but it's going to be one CPU where everything starts, and it starts the bootloader of your program, and it starts running the code, right? So now what you have to do is enable the advanced programmable interrupt controller. The classical interrupt controller on x86, it's what's just called the programmable interrupt controller. It doesn't have the ability to target CPU cores. But this APIC is going to do that. And of course, in IncludeOS, this is something that's being handled for you. You don't have to worry about this. But I'm just explaining what we have to do in order to wake up these cores. So now we have this advanced programmable interrupt controller, and now we can interrupt a core. Is it a good idea to do that now? What's going to happen? I just interrupt the core, I wake it up, and you know, it's probably going to explode because you haven't really given it anything to do, right? And the CPU can't just sit there. Well, it can just sit there, but you have to explicitly tell it to just sit there, to halt it. You know, go down, go sleep. Don't spend any don't waste cycles. So it needs a bootloader itself. It needs a stack, and then it needs something to do. So we give it a bootloader. In that bootloader, we enable paging. We switch to 64-bit long mode. That has to be done in assembly. These are privileged instructions. But then as quickly as possible, we escape into C++. you know, that's a great place to be. So we have a main function for each of these CPUs. You initialize the local interrupt controller for that core so that it too can be able to send interrupts and receive interrupts. And then it has a local timer inside of each core for high resolution timing, etc. You wake up, and then the question is, you know, what do I do after that? I've woken up this core, and we wanted to make an API where it was easy for you to actually just take those cores and make them do whatever you want. So the code, the steps I explained are in these 3 pieces of code. I just put the paths on there. So in case you want to browse this is all open source on GitHub. You can go check it out and see exactly how this is happening. It's the initialization part, and it's the actual bootloader for the CPU, and then you have this main function. So what we decided to put in that main function is an event loop. Yeah, and this code, this low-level code, is done by this kernel developer we have. He's very talented. Please come on Jitter and talk with us if you're interested in more details about this code. So we put an event loop on each of these cores, and incidentally, it's the exact same event loop that we have in IncludeOS itself. So that's an event loop that's going to just ask an event system whether for which interrupts have happened or which events. We abstracted it slightly away so that it doesn't have to be interrupts now. It can also be just soft triggered. You can tell the event system in software that now I want to trigger this event. It just sets a bit in a bit flag. And when you process the events, what happens is that you'll just fetch all the events that have happened and that are subscribed to. And subscribing to an event means attaching a delegate to or giving a delegate to this event system, saying, you know, I want to run this delegate, which can be a stud function or just a normal global function or a member function of any instance you want. So any type of C++ function, give it to an event ID and say, when this event happens, I want this function to run. And you know, when there are no more events to process, we just halt. On x86, that's the halt instruction. It just means go to sleep until the next interrupt, right? So that means you can, when the function is done, you just return as usual. Then it goes to sleep, and you can use a very simple function we have to signal the CPU to wake back up. And that way you don't waste cycles. So we have now these cores. Each of these cores has an event loop, but how can you access it? How can you interface it with these event loops? Seems complicated, right? Event loops? Is it complicated? It's very simple. So this is how you do it. Can you see? Is it a bit dark? I think it's hopefully it's okay. Otherwise, we can do something with the curves. Is it okay? It's okay. Yeah. So all you do is say SMP add task. SMP stands for symmetric multiprocessing. It's just a short for multicore or something in our terminology. So you just say add task. In this case, I'm adding a lambda, and it does some very intelligent work. Okay? Well, it's just a workout. I just want to have a spinning loop. I want to spread it over all these cores just to see that they are active. Okay? But it's very, very simple. This is the API for adding a task to a CPU. If it doesn't have any tasks already, you know, it's going to jump directly onto here. Nobody else is going to give them tasks unless you do so, right? So now we're just saying, optionally, you can add an ID saying exactly which core do you want this code to run on. And in this case, we're just iterating over all the cores, adding one task to each of the cores in sequence. So you can do a round-robin scheduler or some more sophisticated type of scheduling by just giving these delegates directly to all these cores. And there's nothing else going on. And now once we've done that, we can signal it. So I could wait and signal all of the CPUs by just having no parameters. Or in this case, I'm just inside the loop. I'm signaling each of these CPUs so that they start as quickly as possible. And what they're going to do is just wake up, they get an interrupt. The only thing they can do is to process their events. The first event is to process their queue of tasks, because that's the only facility that we've put in place for you. It's just a vector of these delegates. It's going to check that vector. Is there some job here? Okay, there's some job here. Let me execute that. Yeah, and this code is just a workout. But let's see what happens when we boot it. It's easy to boot things. In this case, we have a small configuration file called vm.json. You can tell the virtual machine in this case how many cores you like. If you're booting on a physical machine, I think it's a bit harder. I don't think it's sufficient with a configuration file to say how many cores you want. They have to physically be there. But on a virtual machine, this is how you can do it. And you just say boot dot. This is all explained in more detail in other places. So this is what happens. Okay. So this is on a 72-core Intel machine. It's actually just 36 physical cores with hyperthreading, but they come up at 72 cores inside of Linux. And as you can see, I've started it with 32 cores. All of them are, or all of those 32 cores are each represented by a physical thread in the Linux host. Right? I can go to 50. How far can I go? Anybody know? What do you think? 74. I'll try. 74? 71. Well, that's a good guess. I went to 55 and it blows up. Oh, that's unfortunate. Well, it turned out there's a little exception here. It ran out of memory. We tried to utilize this first megabyte of memory because it's usually just sitting there doing nothing. We tried to put some stats in there, but it turns out we ran out of memory. So that's easy. We could just move those stats. These are just counters. We like to keep the counters in a contiguous memory area, so it's easy to just serialize them. So I moved them to high memory. Now I get to 72. So that was the number of physical cores registered to this host. So that's nice. Can I go further? What's going to happen? How far can I go? Can I go to 100, do you think? 128, no problem. Now I'm overbooking. I'm overbooking the host, right? But from my perspective inside of IncludeOS, I just talk to hardware all the time, you know? And in this case, the virtualization environment has told me that, well, you do have 128 cores. And it's representing each of those cores with a thread. And you can go and count, and you'll see that you'll get 128 threads. We get all the way to 255, and that turns out to be the maximum for Kimo. So I think you can do a lot of things with 255 cores. It's, of course, an open question here. Should you overbook or shouldn't you? I prefer that you don't, you know, but it's up to you. This is one way you can actually overbook. But I think it makes a lot of sense to have a certain track, to keep a certain track on how many physical CPUs you actually have, right? So overbooking is something you should do if you know that you have to do it. So now that we know that all of these cores are represented by physical threads on the host, do we really need another opaque threading API on top of that? Do we? Do you want that? So there's already a scheduler scheduling all these threads, right? So if you're using IncludeOS in virtualization like many people are, then do you want threading and another layer of scheduling inside of there? It seems like it's a bit wasteful. But of course, this guy wants these threads because, you know, it's what he's used to. I understand, you know. So actually, it's mission accomplished for us. It's so simple, I thought, you know, I can fill a whole talk just talking about that. Although I do want to get the message across because I like it. I think it's fun to be able to control those cores. Put a C++ task directly on that core, have it run there, there's nothing else going on. You're in complete control. I like it. But I have to do something more for the talk, so let's look at those threads. So let's try to use this multiprocessor, multicore API and see if we can use it directly to make some kind of Pthreads backend. So this is an attempt. This is just an experiment. It's not something I'm going to go ahead and put inside of IncludeOS. But you could imagine you could make a pthread create something like this. You couldn't just imagine. I mean, I actually did this, and it kind of works, but it has severe limitations. So what's a thread? Well, it has to have an identifier. There's to be a function pointer, and it has to have a pointer to the parameters and a pointer to the return value. So I just made the smallest possible struct, just having those members. Okay, maybe I can get away with it. This is a signature. I can't help that it's like that. It's been that way forever. Can't be changed. So all I do is that, for whenever you want to create a thread, I just have a static counter, increment that static counter, and then wrap the function pointer that you provided. I just put it inside of that struct. Then I put and place that synchronously into a synchronized container that can hold any of these threads. And then I just add task, right? Will it work? I just go to a CPU here, and I have actually a static counter for the task as well, now for the CPU, so that I'll actually do round-robin scheduling now. For each new thread you start, it's going to just go to the next core, and it's going to go modulo around all your cores. So I call the function inside of the task handler, so that means it's going to happen once I signal the CPUs, and then I preserve the return value. So now let's look at join. This is a POSIX join syntax. So I want to join with one of the threads that I'm waiting for. It just means wait for this one thread to complete. So I get an identifier, so I have a synchronized container now. I can fetch the thread from that container. But then the question is, what do I do in the meantime? Because POSIX demands that I should suspend the execution of the calling thread until the target thread terminates. I don't have any concept of suspend or yield or block. What does it mean to make a blocking call if you don't have any thread below you? You're on the core. You control the CPU core. What do you do? What does it mean to suspend? I can either call halt, to halt the CPU, to just tell the CPU, I don't have anything to do right now, so wake me up with an interrupt. That's fine. That's not going to waste cycles, but it's going to leave this whole core standing there doing nothing, right? But maybe you had some other important things you could have done, right? But what are you going to do in software? What does it mean to block? We don't have any concept of that. So that's why this isn't the way we're going to implement these blocking calls. So we save the return value. So yeah, so what I'm doing here is just spinning. What else can I do, right? What else can I do? I can't return. POSIX demands that I can't return, so yeah. So, but it works, and you see here from the output, C0 means core 0, and core 1 and core 2 are running these threads, and they are outputting these messages, and it kind of works, but you don't have any idea of blocking, so you're essentially just sitting there on core 0 and spinning until these other cores are done. Right, so that's wasteful, but well, it's at least if you had to do like 32 in parallel, well, at least those 32 cores that were given tasks, those would be busy doing something useful. Right, so let's go a bit further and let's try to implement something more thread-like in the sense that it can be suspended and it can be resumed and scheduled over multiple cores. So if somebody's thinking boost fiber, that's what I was thinking. It's an idea of this user space scheduled thread, but it's in user space. So they're cooperative, they can yield. That sounds like a way we could do it. You could say yield in a blocking POSIX call. So yield, that would mean suspend and switch a stack. Maybe just a very simple stack switch is something we could get away with. So I tried with, I don't know if I tried with boost fiber or it's so large, these boost libraries. Maybe it was the enclosing library that I tried to build all of that for IncludeOS, and I ran into a pthread dependency. So that's kind of a catch-22. So maybe it could be done, but I thought, well, how hard can it be to implement these fibers? Let me just try. If you're thinking coroutines, you know, could coroutines be a backend for Pthreads? That's kind of a crazy idea. I like crazy ideas, so I'm going to look into that as well in this talk. Yeah. So now do we have to preempt these threads? To satisfy the requirements of the Pthread API, do I have to preempt? There's nothing to say that I have to. Preempt, that just means start some timer, use the interrupt handler facilities in the CPU, or yeah, the CPU has idea of what interrupts are in interrupt handlers. You know, you could set up an interrupt handler to happen on a timer interrupt, and at that point you could save the whole CPU state and then have it resumed, etc. Do you have to have that preemptive timer? I don't think so, because it will introduce overhead. Switching is going to introduce overhead, so why bother this perfectly working core that's busy doing interesting work? So why do a time slice and, you know, force it to not do so? You know, to do something else for a while. What's that going to do to the CPU instruction pipeline? You know, having these interrupts trigger. What's it going to do to the CPU cache? Right? Obviously, if the CPU is expecting to keep doing whatever it's doing and then an interrupt fires, you know, suddenly the whole sequence of instructions that it thought it was going to execute is no longer the sequence of instructions that it will execute. So I think it's better, for performance, it's better to just leave the core doing whatever it's doing until it's done, if you can. Sometimes you can't, but yeah. So we're trying to make a zero overhead operating system, so at least I can't assume that preemption is what you want. I can't assume that, right? It might be what you want, so we might implement that as well, but it's not going to be our first choice. So these fibers, they're non-preempted cooperative threads. We don't need to preserve the whole CPU state. We just have these user space allocated stacks. So we can just allocate stacks using malloc or some other facility. You could have your own allocator, custom allocator for allocating stacks, whatever. But then there's an API for very simple stack switches. So this is a compressed version of the API. This is on a, I think this is upstream in IncludeOS on the dev branch or something. It's not something where I'm not completely finished with it, but it's at least a proof of concept that's out there. We have template constructors. We have many of those. I'd like to evolve those if we decide to go with this and not with the coroutine path. I'd like to evolve this so that it's as flexible as possible. You can essentially just say any type of function signature. You can just give that to a fiber, and a fiber can execute that kind of function signature. But for now, I'm satisfied by having something that can satisfy the POSIX function signature that returns void pointer in it, and it takes a void pointer as parameter. So we have a start function. You can start a fiber. You can yield, and that's a static function, so that in any kind of function you can just say yield. Of course, it's going to imply that there is something to yield to, and we're going to see that. We can collect a return value that's supposed to be blocking. And now we have these private members. We have thread local, which currently, you know, since we don't really have an idea of threads yet, we have an idea of CPU cores. So we decided to implement thread local as CPU local for now. How robust it's going to be, I don't know, but it's a very nice facility to be able to say, I want one fiber to be running on each core at a time. I don't want two fibers to be active at the same time on the same core. I want one for each core. So they are thread local, these fibers. So we have a current fiber, that's the current fiber you can yield into. So we also we keep track of our stack pointer. Remember stack position from where we were. And then we have this jump starter function that's going to just, I'm not going through that, it just makes it easier to call a function of an arbitrary signature from inside assembler. So this is the start function. The only interesting thing that happens here is that I call down into assembly. I'm just saying, you know, this thread is the current thread, this thread is started, this thread is running. Just you know, boilerplate stuff like that. The interesting part is this jump start function, so let's look at that. This is all the assembler that's there to start it. And it's even smaller for yield. It's not a lot. It's not scary, I think. So these are just helper macros to just give names to the registers according to the to the Itanium ABI calling conventions. So it means, parameter 1 is passed on the RDI register, parameter 2 on RSI, etc. So it just makes it easier to talk about these registers inside of the code. So this is something you're supposed to do when you're using the calling conventions. These are the registers according to the Itanium ABI that you're supposed to preserve. So you have to do that, simple macro for doing that. But then we go to the actual code. Preserving the stack pointer is just a move operation. So I move the RSP, that's the stack pointer register in the CPU, move the contents of that into the pointer that you provided. Okay, so we can save the current stack position in the pointer that you have provided. Now I actually just switch stacks. I just say, well, what's on parameter 1, the parameter 1 register, just put that right into the stack pointer. We also push a stack frame, shift some arguments around, and then we actually just call this jump starter function. All it's going to do is call start on the fiber that was the middle parameter there. Okay, it just makes it easier because then you have all of C++ when you're doing the call. So it also means we have a nice C++ stack frame that we can use. So that's all. And then once we return from that call, then we're going to switch stacks back. Right? That's all. And this might be in use on another CPU. Right? So you switch back into a stack. If that stack is already active on another CPU, obviously there's a problem. So we have to avoid that. But this we want to do as little as possible inside of assembly, so this is all. So what this actually turns into, it's a sideways function call. So you have main, then you call start, and you can see that at the bottom of the stack frame we keep track of the return value. So I don't, in my little thread implementation here, I don't need to keep track of the instruction pointer myself because that's already inside the stack frame, right? So the stack frame of the caller that will keep track on where I'm going when I'm returning. So, and then we do a normal function call into fiber jumpstart, then we switch the stacks. So we actually just start with a completely fresh stack and there's no return value at the bottom there. But we ensure that, inside of the stack frame, the last piece of code that's going to execute before you get to a return is going to be a stack switch. We saw that from assembler. After the return, you switch back to another stack, and then you pop off the instruction pointer and jump there. So now you can do something else. You can call whatever. And you can return. If you want to return to the caller, if you didn't change the pointer in the meantime here, if you just let the pointer be the same and unmodified during the execution of this fiber, then it's going to just return back to wherever it came from. And that's a normal stack frame. So of course it's dangerous. In this case, I'm just showing that it can go really bad, if you switch back into a stack frame that's in use already. So of course I struggled a bit with that because I made this fiber implementation for a single core in the beginning, and then when you extend with many cores, you get into these kind of situation. But it's not that hard to fix, and essentially just having the thread local or the CPU local in our case current function, and make sure that whenever you resume on one CPU, that CPU has to tell the resumed fiber where it's going to yield to next time it yields, right? So you kind of give it a new parent fiber whenever you execute it on another core. So of course this would blow up. In this case, I would switch stacks into the middle of a stack frame where somebody else was updating the account balance of some bank. Maybe I would then just go right ahead and release a mutex that was locked. All kinds of bad things can happen. So of course you have to be careful, but it's not that hard. So hopefully you do something sane. So now look at the code for yield. We say current is now, we actually give ourselves a new parent, and we say the current CPU local or thread local, the thread that's currently running, that's now our parent, so that that when we do this fiber yield, this is where we want to yield to. And then we do this fiber yield call, which is just a stack switch. And in the resume, it's actually the same. But we are now saying, now we want to make a new parent as well. So we're saying now, I want the current fiber that's running on this CPU to now be my parent, so that when I'm done, when I return to that fiber. And then we do the stack switch. And look at the code for the stack switch. It's just a stack switch. It's nothing else, right? And this works. This I'll show you. So it's not scary, a lot of assembler. Of course, it's very powerful. You can do a lot of wrong with it, but it's also quite simple so that it's not that hard to get it right. So we just save the stack pointer, and we just restore any stack pointer that you provided, right? So you give it 2 parameters. Which stack do you want to switch into? Where do you want to save the current stack pointer? That's it. So then we return to wherever that stack was going. So now you can actually suspend the tall call stack, right? Because in the first illustration, I showed you the return path, but now we're going to look at the yield path. The yield path is actually more interesting in terms of creating a blocking call, right? Because you don't want to be able to you don't want to have to unwind the whole call stack in order to do a blocking call. You can't. You have to be able to suspend a tall call stack. So with this yield call, you can do that. You just do a yield. It just switches the stack into somewhere else, while a lot of these stack frames are already underneath. So now you can unwind this stack, and a reasonable thing to put on the bottom here is the thread runner or something like a scheduler, so that whenever you yield, you go back into some kind of scheduler. That scheduler can then ask you, are you done? You're not done? Well, then I'll give you another chance and resume you. And then that can resume something else, and we can do this across CPUs. So let's look at scheduling N fibers over M CPUs, because that's something I thought was kind of useful about having some kind of threading abstractions. Is that maybe I don't want to hard code this to have to count the number of CPUs, or to have my tasks split up into chunks that already fit the number of CPUs. So maybe I'll just split the tasks into tasks I think are reasonable for the job I have to do, and then spread them across any CPUs that I might have. So I'm just making a little worker fiber here as an example. So the job of this worker is going to copy an array of strings from A to B, from source to destination. It's just a dumb copy, but I want to do that copy operation in parallel. And just to make it more interesting, so this way I can partition which worker is going to do which string copy. So I'm giving it a parameter, and I'm using that parameter as an index to figure out which of these strings am I in charge of copying. So I added some extra work. You'll see why in a minute. Because it's quite interesting that I want to see the CPUs actually do work, but I also want to be able to measure the overhead. I want to compare fibers versus coroutines to see which is faster. In that case, it makes sense to have a job that's so simple that you're certain that the stack switches are going to be more work than the actual busy work. But I also, of course, want to do some realistic stuff here. So I have a volatile counter that just means before I actually copy one character from one place to the next, I just iterate and actually search for that character. It's completely useless, but it's a way to be able to stress the cores by turning off on this switch. So this is the actual copy. It's a completely normal copy, and then we do a yield. So copy 1 byte, yield. Copy 1 byte, yield. Right? Great algorithm. So this is an atomic job tracker, just so that these thread runners can make sure and figure out if there are still jobs in the queue. So we have a synchronous queue of fiber pointers. So it's synchronized. It's just a simple lock guard for insert and for extract. So we put all these fibers inside of there. And now we populate the source string with random characters. And then we just add one worker per string. And you see here I'm constructing a unique pointer to a fiber, and I'm giving it a worker to say that you're going to run the worker function. And then this is the index that you're going to use as parameter. That's actually the string you're going to be in charge of copying. So one worker per string to be copied. So this is the thread runner. It's quite simple. It's just a loop. The idea is to put one of these runners on each core. So all it does, it's synchronously getting on a job, if there are any more jobs. So it's synchronously getting on a job from the queue. If there was no queue, I could now halt. That would be a reasonable choice to say, well, there is no jobs for me. I could just go to sleep right here. But in this case, we're just busy waiting. So I resume the fiber. If it wasn't done, then I just put it back into the queue synchronously. So that it's ready for any other CPU runner to fetch it and start running it. So this is the task. So we're actually adding one runner for each of the CPU cores, and we're starting them, and that's all. But you didn't see any signal. So I added tasks to the CPUs, but I didn't fire an interrupt to the core to say, now you can start working. I didn't do that yet. So that's what we're doing here. This is just a test setup. I'm calling this assigned workers, putting workers into the worker queue, and I'm assigning runners, having one fiber runner on each of the CPU cores. And then I take a timestamp, and then now I fire the signal to all the CPUs at once. So all the CPUs are going to wake up, start doing their thread runners. And okay, so I'm now wasting some cycles by having this number one core just busy waiting until all the jobs are done. You could easily do something else, but this is the easiest thing to do for an experiment. So we verify at the end that the copy was actually done correctly. In advance, I actually also verified that the copy wasn't done because I was so afraid of the compiler optimizations that I thought, maybe they actually realize that I just want the copy, so they don't even do the copy. They just output the source string instead of the destination. So I do verify that this actually gets done. So this is the output. So that's okay, it works, but that was 32 cores and 32 strings. So I had 32 strings, so essentially I had one string copy per core. And I did it byte-wise, and I yielded. And you can see that this number of insertions and extractions, it's correct if you calculate the width of the string multiplied by the number of strings. You can see that I actually yielded, and I was suspended, and I was put back into the work queue for each byte I copied. But it was one-to-one, right? So I wanted to have this abstraction where I could just say, I want this many jobs to happen, I want to have them happen on any cores you might have. So we increased the number of cores, and that works. So we do with 2 cores, 4 cores, 8 cores, 16 cores, and 32 cores. And it's great, the time it takes to perform the work increases with the number of cores. That's correct, right? Is what you wanted? Excuse me? Sorry, I don't...
What are the units?
Oh, the units in this case is seconds. So this is all wrong. This is all wrong. The number, the time it takes to complete this string copy isn't supposed to increase with the number of cores. That's completely opposite, right? But it's correct because copying just one byte between each, I'm copying one byte and then yielding. So I'm being inserted back into the worker queue, taken out of the worker queue, doing the stack switch, and of course all of that is going to be more work than copying a single byte, which is the busy work, right? So the amount of overhead is of course much, much higher than the amount of work. So that's why I had the extra work put in there, you know, this volatile integer that I forced it to actually do some heavier computation. And you know, if you do that, then you get exactly what you expected. You get kind of an exponential decrease in work with respect to the number, of course. Yeah?
Do you increase the work size? Like, do you do more strings when you do more cores?
No, I didn't.
Oh,
sorry. Do I increase the number of strings when I with more cores? No, I kept it at 32. So it's 32 strings, and I'm copying them with 2 cores and 4 cores and 16 cores and 32 cores.
But isn't then the overall number of yields independent of the number of cores?
It is, yes.
But then why does it get? Then I don't get why it gets slower.
Okay, we can talk about that later, but because I want to also be able to demonstrate the coroutines, but at least this is somewhat what we expected. We get exactly exponential, or you can see that 16 cores it took 4 seconds, 32 cores it took 2 seconds. So what was interesting is I didn't change the code, so I just changed the number of cores. Fibers were suspended and resumed on many different cores. So we had true parallelism, but we didn't do any preemption or any Pthread interface. We used pure C++ and some assembly all the way down to these cores. So that was quite good. Now let's try with coroutines, just because it's interesting. Have you looked at the coroutines, played around with it? Yeah, I'm not going to be able to explain in detail what they are. There are much better talks suited for explaining the coroutines, but I'll just show you a very basic one. And we'll repeat the experiment with coroutines. So this is an awaitable future. So that's actually the representation of a coroutine, or the return value of a coroutine. But that controls the behavior of this coroutine. Oh, 5 minutes left. So I'm going to have to do it really quickly. We have a coroutine handle, move-only semantics. Whenever you want to get the value, I resume the coroutine. And then what should happen if somebody is waiting for this coroutine? That's controlled by this function here. So when somebody is waiting for me as a coroutine, their handle, or actually their coroutine handle is going to be passed into me. So the caller actually gets control of the callee. So I can decide what's going to happen here. And you know, the simplest solution is just to resume the coroutine. Whenever the coroutine is resumed, then I can resume whoever was waiting for that coroutine. That's the simplest way. And you know, we could pass this handle, the coroutine handle, to another core. And you know, we're going to do some experiments with that later, so that you can have something whenever you create a coroutine or just call a coroutine, it's going to automatically just end up on another core. But that, you know, that means you might have races on the coroutine handles, etc. So you might have to synchronize these objects, etc. So I thought it was, for this experiment, I'm doing something very similar to the fibers. I'm just creating the coroutines and having both the coroutine and the one waiting for that coroutine to happen on the same core. Okay? So I have a yieldable promise type, and this promise type is kind of a policy for the coroutine execution itself. It just says, you know, when should you yield and when should you, or when should you suspend and when should you not suspend. So in this case, we're saying, you know, whenever you construct the coroutine, don't start executing the function right away. Just, you know, suspend always. So that means you can construct them in advance, put them in a container, and then, you know, trigger the execution at some later point. Update the value and suspend on co-yield. Now that's interesting is that now we can actually control the execution of yield. So you could actually say, whenever the coroutine yields, you can say suspend never. Right? So that's a nice way to say, if I just want this coroutine to stay busy and just, you know, it's yielding between all these character copies, that's kind of stupid. So maybe we just assign it to a core and let it work until it's done, you know? And it's going to go much faster if you do that. But of course, you don't yield, so you don't share work then. So, but it's nice that you're able to control the operation of the coroutine like that. So This is the worker and the assigning of workers and the runners, and it's actually completely identical as to the previous code, except I'm replacing fiber yield with co-yield. And now I'm also be able to yield with some value, some intermediate value. In this case, I'm just saying which position I am in the string. I put them now in a queue, so this is now also identical, except that it's now a unique pointer of futures instead of unique pointers to fibers. So everything else is identical. Now, instead of starting the worker by constructing it and passing the parameter, I'm actually doing a function call here. You know? So I'm actually doing a call to the coroutine. I'm saying worker with an index. But the return value of that worker is a future of this type, and this future I've described that whenever you construct this coroutine or whenever you start it, it's going to suspend right away. So it's never going to get started right off the bat. So it's kind of funny syntax, but it makes sense if you play around with it. So the rest, the runner thing, is completely identical. I synchronously get a new coroutine from a queue, but instead of fiber resume, I'm now saying co-await. So I'm waiting for this next job. So that's going to return to me whenever it returns or whenever it co-yields. So the runner is also the same, but now I'm saying, instead of constructing the fiber and saying fiber start, I'm saying that I want to run a runner and get its return value. So the setup is actually identical, no changes in the code at all. We just have all this, assign all the workers and all the runners, and then we signal all the CPUs to wake up, start executing the runners. Runners are going to fetch workers out of their queue and then start executing those. So identical output, copy was verified and timed. We have similar thing. We'll have to think about why this is the case. If you don't have any work, you just have the overhead. Why does the overhead increase with the number of cores? We'll have to think about that later. But once you do the busy work, so they actually have something to do, then you get a very similar graph. They're so similar that you actually almost can't see that both the graphs are here, but this is the hard work for fiber and the hard work for coroutine, and you can see that the graphs are very, very, very similar. But I want to find a winner, right? I actually don't want the fibers to win, because it would be so nice to have these compiler-assisted coroutines and just use that as backend for anything in parallel, right? So let's do 50 runs for 32 cores. Still not that clear who's the winner. So I did a two-tailed, two-sample t-test, you know, to get a statistical idea of, you know, is there a significant difference in means here? Is there a statistically significant difference in mean? And unfortunately, it wasn't. So let's do the one that doesn't do the hard work, that does the easy work, and will increase the number of runs. So I did that to 150. Still can't see a clear winner, but the statistics come through, and now we have a significant difference in means. Okay? Well, that's great. So we actually know that it's not that easy to see, but we know that the green ones, you can see the green ones are the coroutines, and they're actually faster. And if you look at the means, of course, it's quite obvious. But it's unfair to compare means unless you know that they are significantly different, right? Because you saw there's a huge amount of variation here. It's caused by, of course, the fact that I'm running on a Linux host. So could we use coroutines as a Pthread backend? The problem is that they can go only up or down. So to implement, so I find them great. They're a lot of fun to play around with. You see that you can schedule them directly onto CPU cores and treat them exactly like you would these fibers. Am I out of time? Okay. So the only thing that's, so it's really good if you have everything is coroutines all the way down, then it's fine. But you know, if you try to actually, if you're really forced to implement something like fread and you're forced to actually block, then you have, you know, rules from POSIX that states, you know, you're not allowed to return from here. But when you suspend a coroutine, or you wait for a coroutine, and that coroutine suspends, it's going to return control back to you. So you have to kind of be prepared for that. This could be an intermediate value. So if you're not, unfortunately, I don't see how you could escape this stack. You could either go up in the stack frame or down in the stack frame with the coroutines. Even if you suspend, you're going to unwind the stack. Whereas with fibers, you're able to do this sideways function call and switch and actually suspend the whole call stack. So who should be in charge of the stack pointers? Should it be the operating system or the compiler? I think the guys who are putting in the canaries. I'm very grateful to those. Do you know the stack protectors? You run into those stack protectors now and then. I did, of course, when I implemented the fibers. So I think they're doing a great job of protecting my stack. So I think the compilers are very well equipped to take care of the stack pointer. But while the compiler is evolving, of course, we'll do what we can to help. So, yeah. Conclusions: you don't need classical threads to utilize CPU cores. You can run fibers and CPU cores or fibers and coroutines directly on them. Pthread backend requires true blocking. We can achieve that with the fibers. I don't see how you could do it with coroutines today, but I'm hearing rumors that there will be stack full coroutines as well. In that case, we could use those as backend for Pthread, or actually drop the Pthread altogether. So it's been fun to work with this. Expect more of this from IncludeOS. Any questions? Please contact us. Yeah. Are we?
Do we have time for questions? Okay. So, unless I misunderstand coroutines, they basically always allocate dynamically to keep track of the state that they need to restore. And it's just compiler optimization if they manage to ally this allocation. So I was wondering if your fibers do that as well, because as far as I can see, they really don't have that explicit allocation. So maybe you just got lucky in that example with coroutines, and you got heap elision. So
it could be that I was lucky, but I also noticed that the coroutines are much better at optimizing when it yields or not, or when it does anything. The problem with my implementation, of course, is that I'm forcing a stack switch unconditionally. There's no way for the compiler to remove that because I'm doing a call into this opaque assembly function. So it really can't optimize it away. So for situations where you see coroutines doing something that's actually wasteful work, you will see that the compiler is good at just optimizing that away. And actually, the first experiment I tried, I got this coroutine result that was like 500 times faster, but that was just because the compiler just saw that, oh, this is just wasteful work. I don't have to do any of this. So for me, it's obvious that compiler can optimize coroutines to much more extent than it can optimize these fibers because the stack switch is opaque, and I think that's very promising. What's the trade-off between this allocation and the stack switch? That probably depends on the use case. Do more measurements and experimentations. Stackfulness is missing, yes.
You have essentially fibers implemented at the operating system level by giving them a stack.
Yeah.
How is that not a classical thread?
How is that not?
Just a classical thread that
Oh,
you're saying you're not doing.
Because this thread can't be preempted.
It cannot be?
Well, I could, but I haven't made any kind of an abstraction to be able to save all the registers and to save the. Usually, if you look at the task structure for Intel, you will see that it has a couple of stacks. It has one stack for each protection level, for example, and it will actually preserve the whole CPU state into a separate area of memory. So it will preserve everything: floating point registers, everything. For example, I'm not preserving floating point registers because I'm just relying on the calling conventions of the Itanium ABI. So I know that whenever you do a transition from one thread to the other, your stack frame is in a very healthy state. So that's how they differ. But there's nothing to say that I couldn't make a timer interrupt handler that preemptively preempts this CPU that's running the fiber. I could certainly do that, but I would need some extra work around it.
Yep, thank you.
Yeah.
I saw that you used std atomic in your example.
Yeah.
Did you implement that for arbitrary types, and if, how?
I didn't do anything. It just magically just worked.
Okay, I thought with arbitrary types it would be based on something like a mutex or so.
Oh, right, right. So I did use a mutex, and we did implement the backend for a mutex as a spin lock.
Ah, okay.
So, but then the atomic integers that I'm using for counters, I didn't have to do anything for that. I'm guessing that it used like compiler intrinsics or something to just, you know, store atomically. Yeah. So that was in the library.
Okay, I'm afraid we are out of time, so
Sure.
we'll have to stop.
Thanks a lot.